And it's coming up to 12 minutes to 8 o'clock. You're listening to the Environment Show on 3D Radio, broadcasting on 93.7 on the FM band. And in the studio with me is Professor Derek Abbott from the University of Adelaide in Electrical Engineering Department, I believe.
Yes, that's right. Good day, Roman.
Hello, Derek. I asked you to come in here because of a talk you gave a couple of weeks back at the university, which sounded very entertaining indeed. Rising to global power. What was that all about?
Well, what I was talking about was looking at all the various forms of energy generation that we have in the world, like oil and coal and gas and nuclear, and looking at all the options and also the renewables, of course, and looking at them each one by one and just testing them one by one and asking the silly question, can one of these on their own supply the whole world's energy needs?
Now, that's a very interesting question. It nicely leapfrogs this pointless debate about the emissions trading scheme and gets down to the heart of the matter because, of course, you're trying to figure out if they can do it in a sustainable manner.
That's right.
How did you define sustainable?
Right, that's an interesting question. So I didn't actually, it turned out I didn't need to get too strict about that definition. What I was able to do is take each power source on its own and eliminate some of them for very trivial reasons. Like I can eliminate, for example, nuclear fission straight away because according to the World Nuclear Power website, so I've got their own figures, I haven't cheated and use the figures of a competitor, they say themselves they're going to run out in 80 years. So now if you ask the question, what happens if you supply the whole world's energy needs with nuclear powers, it only lasts 5 years. It's ridiculous. So we can immediately eliminate that without any questions of it's just so blatantly stupidly unsustainable.
Well, it does beg the question, what happens if you move to a breeder reactor, which presumably increases your source 100-fold or more?
Yes, I'm not convinced that technology is viable because as soon as you start going to different elements and trying to breed, it gets more complicated. But yes, that's an interesting question I will have to address in the near future.
The obvious question, coal. Not sustainable because of the greenhouse effect.
Yes, yeah. And according to the the oil and coal official website, they say themselves with their own figures that it'll only last 130 years at the present consumption.
Right. So even if you had clean coal,
yeah, even if it was magically clean tomorrow, it would only last 130 years. And oil is even more scary. According to their own website, 40 years. Or it was 42, sorry, to be accurate. And I am writing up a paper about this at the moment, and in my paper I'm making the point that we urgently need to get off oil straight away. We can't wait 40 years. We have to start making the transition now.
And obviously there are better things to do with oil than burn it.
Yes, and it's not. And my argument is nothing to do with the cleanliness of oil or whatever, or the dirtiness of it rather. It's to do with the fact oil is extremely useful. We actually need it to lubricate engines and machines. That is part of our everyday life. And we need it for lots of things that we don't use it to burn. And if we wait 40 years and burn it all, we've got no oil. What are we going to run engines on? What are we going to lubricate the engine on, rather? So I think we urgently need a solution.
Okay, so we've eliminated coal because it'll only last, if we're lucky, 130 years.
Yes.
So what sort of time span are we looking at if you want something sustainable?
Well, that's an interesting question, and I guess that goes back to your first question about how I define sustainability. And so I did a rather futuristic, have a rather futuristic view on this. I define it as 1 billion years, and the simple reason is that in 1 billion years' time, the sun grows to a sufficient extent on its progression towards becoming a red giant.
Yeah.
It doesn't completely become a red giant in 1 billion, but it starts.
Yeah, and we're talking growing out to the orbit of Jupiter, I think, ultimately.
In 1 billion years, so the astronomers say, it will have grown sufficiently that it will have boiled us all on the planet. So we will, in 1 billion years, we will have left the planet anyway. So I define sustainability as 1 billion years. So when I'm going through all the different fuel sources that we have in the world, I'm looking at what can last for 1 billion years. And clearly coal, oil and gas are just a tiny blip on the time scale.
So how much energy does the world currently need? Currently use? And let's not say need. How much energy do the people of the world currently use?
Yes, as a human race, we are consuming 15 terawatts. Now, just to remind people what that means 1 million watts, which is the quantity of energy used per second. Just, I guess, to give a feeling of what 15 million watts is, how big that is.
So a terawatt is 1,000 gigawatts.
Yes. So to give a bit of a feeling what these powers mean is what 1 watt is actually would be like a torch, a flashlight. And so if you had 1 million flashlights and put them all end to end, it would go from one end of the solar system to the other. That's how long they would be. So it's a big number. Then 1,000 watts is something like your humble electric kettle that you use in your kitchen. Of the order of megawatts, like 3 megawatts would be something like a diesel engine. 50 megawatts is the power consumed by all of Google's computers. So every time you click search on Google, you're connecting with a whole network of computers that suck 50 megawatts. And so on. The Hoover Dam is an interesting example of a gigawatt. The Hoover Dam actually gives you 2 gigawatts, which is 2,000 megawatts. And so on. And so when we get to the scale of thousands of gigawatts, that's what we call terawatts. So 15 terawatts is the whole world's consumption.
Have we got anything that operates at that scale?
Oh, you mean an energy source,
yes.
or an example of something?
An example of something.
That sucks something in the order of terawatts?
Yes.
That's an interesting question. Yes. The whole world's photosynthesis of all the plants on the planet use 75 terawatts. Mm-hmm. So that's considerably bigger than 15 terawatts. So humans actually use a lot less than plants, which is very interesting.
Just as well. So that does raise an interesting question. I mean, could we use photosynthesis as a source of energy?
That's an interesting question. And in my talk, I said no, because you see, when you burn a plant, apart from the fact that when you use that biomass, you're going back to the old hydrocarbon scenario, which we want to try and get away from. Apart from that, I mean, there's an extreme efficiency loss compared to the energy that went into growing all those plants, which is 75 terawatts, to what you actually get out. So if I burnt all the plants in the world that grew out of this 75 terawatts of sunlight, I haven't actually done the calculation, but I guess the amount I would get out would be a tiny fraction of that. Off the top of my head, 1 terawatt or something. So it's hardly worth it for all those hydrocarbons you're burning.
And not to mention the soot.
And the soot, yes. And one has to put all these things in perspective and look at what's worth doing. If that was all we had, sure, maybe that's what we have to do, but that's not the case. We've got something cleaner and much bigger out there, which is, of course, is solar energy. It turns out that when you analyze solar energy, the power output that comes out of solar energy is so huge that all other renewable sources, whatever they are less than 1% of what we can gather from the sun. So all these other renewable options like geothermal, wind, biomass, waves, all those things, they're all less than 1% of sun. So what my point in my talk is yes, hey, these other extra sources may be very well may be fine if you're living in Iceland where there's hardly any sun. And to give out the Icelanders some credit, they're doing a very good job of making a little sustainable energy economy there out of renewable sources that don't involve much direct sunlight. And so that's great. But when we're talking about the bulk of the world, we have some fantastic, huge deserts, expansive deserts. And I've calculated that you need less than 8% of the world's deserts to actually power the whole world with sunlight. It's a very small fraction.
Now, it's interesting. You did raise the question of how much of a total consumption could sunlight provide in your talk at the university.
Yes.
And you gave, I think, 4 options.
Yes.
Starting out from, is it enough to power New York City?
Yes.
Is it enough to provide half of our requirements? Is it enough to provide all of our requirements? Or is it enough to provide 10,000 planets worth of requirements? And the answer did seem a little unexpected.
Yes, indeed.
I mean, some people might suggest it's enough to provide the whole planet's requirements, because obviously the whole planet does run on sunshine, whether it's fossilised or otherwise. But in fact, the conclusion you came to was extraordinary.
Yes. In fact, as you said, the sun actually provides 10,000 times our whole world's energy consumption consumed by mankind, which is absolutely huge. So this is obviously the option we should be focusing on, rather than playing around with wave power, which is a tiny, tiny fraction of that. You see, the world has limited resources and limited funding for research and putting money into things. And if you've got one energy source that's absolutely clean and is so huge, that's the one to go for. Why are we wasting money on minor renewables, unless you're Iceland, of course.
Now, we should mention here that, of course, that 15 terawatts is our current consumption.
Correct.
And one of the big arguments in the whole climate change issue is, well, what happens when the developing countries, if they follow the same fossil fuel-based development path, how much energy would we need if everyone was living at, say, the typical Australian standard of living?
Yes.
And I presume you've done some kind of calculation.
Yes, I've done some interesting calculations about this, and so I've basically prefaced my whole talk and also my paper that I'm writing with the point that we can't just be cavalier with energy. Okay, so we've got 100,000 times the amount of energy we need coming from the sun, but we can't just sit on our laurels and say, okay, we've got so much energy from the sun, we don't have to worry about energy anymore, let's just go sucking it all up and go crazy. You can't be cavalier. You still, at the same time, have to be very conservative with energy. You have to conserve energy and be very careful with it. And so I'm proposing a two-pronged approach, both energy conservation and go solar. Now, with energy conservation, the calculations that I've done to show how crucial that is, I've done a couple of very interesting calculations. I've just assumed an average house, if you add up the surface area of its walls and its roof, is 500 square meters. That's the surface area of the outside walls of the house. And I've assumed, just for simplicity, get rid of all the complicated factors, that it's got no windows or doors. This is just for an energy calculation, just to keep it simple. And I've just assumed that its thermal conductivity is 2, which is about the thermal conductivity of brick. and just assume that we want to maintain a temperature inside the house that is 5 degrees different from the outside temperature. How much energy would that take? And how much energy would that take if there were a billion such houses in the world? So every family of 5 in the world has got one for 5 billion people. So I'm giving sort of equality for the whole world here in this standardized house. And the amount of energy that comes out is absolutely enormous. It's something like 175 terawatts. It's like over an order of magnitude bigger than our present world consumption. We simply cannot afford to build houses like we're building them in Australia at the moment. They're absolutely crazy. I hardly see any houses in Adelaide with double glazing or cavity insulation in the walls. The government has to wake up and start putting incentives to get houses properly insulated. And I think this is step number 1. It's a huge one, and then we need to look at also all the other forms of conservation that we can do.
So clearly, if we continue wasting energy, if you replicate that on a global scale, there's just not enough to go around.
Exactly. It just well, there is if you take the solar energy viewpoint, but there's just not enough to keep doing it for 1 billion years. But and it's just crazy, just losing 175 terawatts just because all the houses in the world are not insulated properly. You've got to be sensible. Another interesting calculation I did, and this is actually one you prompted me to do, so you inspired me to do this yourself, is I calculated what would happen if everybody just drove a car for an hour a day. You asked me to calculate what would happen if they just went for a kilometre to the shops and back, but I decided to pose the problem different. It's the same thing, just drive for an hour a day. And I assumed an average engine size of a 50 kilowatt engine. And if everybody did that, it turns out to also be quite a huge number. It turns out that also of the order of 175 terawatts will be consumed. So that's absolutely enormous. So what that means is you can't expand the transport network that we have in the West to the whole world. It's just such a huge number. To keep global equality, I guess what one has to be thinking in terms of is people sharing transport, using public transport as well as cars, and the more you do of that, the more it goes around. And of course, if we do change to a complete solar economy, we can in fact supply quite a lot more expansion than we can do at the moment with just oil. But I think the bottom line message is that we need a combination of two things. We need to get away from oil and use solar so that we can expand to some extent, but we also need to be looking at conservation and how we can use cars as little as possible if we can, if we're in that position to.
Yeah, Amy Lovins used to talk with his briefcase, and he basically pointed out that if we all swapped to the currently most energy efficient lights, motors and engines, we could reduce our electricity consumption to a quarter of what it currently is. Not making no changes to lifestyle, just swapping in efficient lights, motors and engines. So clearly there's a lot of room there for energy conservation.
There's a lot of wiggle room for conservation, yes, and we need to start now.
Now, we've come to the conclusion that solar is the way to go because all the other renewable forms are basically indirect solar.
Correct.
And the order of magnitude of insulation, the amount of solar energy striking the planet is just 2 or 3 orders of magnitude larger than any other renewable.
That's right. And wind power is essentially solar energy with a 99.9% efficiency loss. If you look at it like that.
Well, yes, put it that way, yes. Okay, so we've come down to solar. Now, the question is, what kind of solar? Because there are obviously various ways you can use the sun. I mean, there's everything from your solar hot water, which is basically a metre of black plastic.
Before I get to that, can I make just a few small points about the other renewables? Apart from them just being less than 1% of solar, they do have some problems, like wind power. If you think about wind power, the wind turbines have to undergo a lot of battering from the wind, and so the bearings get extremely hot in the wind turbine, and that has to be it has to have sump oil that is actually cooled to make the wind turbine work. And I worked out what would happen if you supplied the whole world's energy needs with just wind only. And it turned out to be something of the order of you'd use something like 30 million barrels of oil a year. And this is assuming you change your sump every 5 years. So I was being very generous here to wind. And that's an enormous amount of oil. Now, it's not that enormous on today's oil production levels, but in 40 years' time, when oil's running out, that's a lot of oil. So I think wind power is unsustainable from that viewpoint. Hydroelectric power is fantastic. It presently supplies 20% of the world's needs, for electricity, that is, electricity only. And I see that still continuing, but it's clearly not going to supply all the world's energy needs because of you need a certain number of strategic waterways. However, there is some wiggle room for hydroelectric to increase. The whole world has 45,000 dams, and only a quarter of them are used. Presumably, some of them aren't maybe cost effective to use, but so I'm not suggesting that you can still use 3/4 of them, but I'm sure some of them still can be. There's ocean thermal gradients because the ocean gets hot, and there's potentially 100 terawatts in the ocean, but it turns out you can't really efficiently harness that power because the temperature differences are very small. They're only of the order of 20 degrees centigrade.
So we're up against the zeroth law of thermodynamics here, aren't we?
Exactly.
Which basically says that the larger the temperature difference between your two bodies, the more effective work you can...
The more efficient you are, yes. So it's a very inefficient form of getting power. Then there's geothermal, and we've already discussed that. It's extremely sustainable. I've calculated that if we got 1 terawatt out of it, it would last 3 trillion years.
That's not bad.
Because the Earth actually has the heat energy inside the Earth is something like 10 to the power of 31 joules. It's absolutely huge. But the catch with geothermal is it's very diffuse around the planet, and you could probably only get really 1 terawatt out of it maximum. So it's great for Iceland, but not for here.
It might be good for South Australia as well. Apparently, we do have some good hot rocks that we can look at.
But we have a lot of hot desert that maybe we should be investing in for solar power, as I'll indicate in a second. So that was a quick Cook's tour of some of the other renewables.
Wave power?
Wave power, again, it's absolutely tiny. It's 0.003% of the amount of power you can possibly get out of solar. So, if I'm a politician, which I'm not, but and I have a certain bag of money, a certain budget, obviously I'm going to put my budget where the big money, big power is, rather than the 0.003%. So that's the way I would look at it if I was a politician.
Yep. Now, when we're talking solar, there are really basic 2 strands. There's either photovoltaics or what's called solar thermal.
Correct.
Basically, directly heating from the sun.
So let me weigh up those 2 and tell you what I think of them. I ought to add there are other funky ways of gathering energy from the sun, but we're going to skip over those because... basically, it would take all night to talk about them all. And basically, the solar cells and the solar thermal are the 2 main contenders. So let's talk about the 2 big boys in the boxing ring, and I'll talk about which of these 2 I think is going to win the punch-up. Okay?
All right.
So let's start with solar cells. So As everyone knows, solar cells tend to be made of silicon, so it's a semiconductor. And what I've calculated is, assuming a certain average solar irradiance per day of, say, something like 300 watts per square meter or something of that order, it would take 100 by 100 kilometers of solar panel area to supply the whole world's energy needs. That's something like 4 times bigger than the area of whole state of Victoria. It's absolutely huge. And then what I did is calculated how much water and chemicals you would need to actually generate that amount of solar power area. And it turns out that it's absolutely huge. In fact, it's so big that just the amount of arsenic you would need to use, because semiconductors have arsenic dopant in them, would actually exceed the whole world's supply of arsenic. We've only got something like 1 million tons of it, and we would need 6 million tons to make that amount of solar panels. So straight off on the resources viewpoint, you can cross off solar cells right there and then.
Does that also rule out things like the disublimated cells that are just starting to crop up?
Well, you see, the problem there is then you've got an efficiency drop when you go to that sort of technology. I haven't done calculations for that particular solar cell type. I've really just focused on what the main contenders are. So another reason to cross off solar cells out of the game is that really when you look at them, they don't exploit the law of thermodynamics that we just talked about a moment ago.
The greater the temperature differential, the more efficient
the more you get towards thermodynamic efficiency. They don't exploit that. Let me explain why. You see, it turns out that if you focus the sun down to a point, say with a 10-meter wide mirror, a curved mirror that's 10 meters wide, at that focal point you can get temperatures as high as 1,000 degrees C. It's huge. And so to fully exploit the power from the sun, you need to exploit that temperature difference, that 1,000 degrees C. That's what thermodynamics tells us. Now, a solar cell can never actually do that, because what happens is a semiconductor can't survive at those sorts of temperatures. It would have reliability issues, and it would have problems with leakage currents, which exponentially increase with temperature. So a solar cell is never going to get that kind of efficiency of a technique that exploits that 1,000 degrees centigrade that you can get out of the sun. So I cross it off for those two reasons: a resource reason, the amount of materials that you have to put, toxic chemicals you have to use to make the solar cells in the first place, and the thermodynamic efficiency viewpoint. Going back to the toxic chemical thing, I'd like to point out that when I calculated how much water you use to make that amount of solar cell and how many chemicals, and then divide the number of grams of chemicals by the number of grams of total water, there's some huge numbers involved here that I can't remember off the top of my head, but I remember that when I divided the two, I got 400 parts per million. So you're creating this huge volume of water with 400 parts per million of toxic chemicals in there. And when you're talking semiconductors, you have to realize there's some pretty nasty chemicals in there. There's things like hydrofluoric acid, and in my paper I'm writing, I'm referring to a website that actually lists all the toxic chemicals. I can't remember them all off the top of my head, but there's a huge inventory of them, and the interested reader can go to that and see what's involved there, and it's pretty frightening. So that's solar cells. So what is the preferred way, in my opinion, to collect solar energy? And I think this is the main contender in the boxing ring that I think is going to punch out solar cells with a straight left hook. And it's what's called a solar thermal collector. And so what that is you can imagine a curved mirror, a dish if you like. I'm sure your listeners have seen the movie The Dish, about using an astronomical dish. So imagine one of those dishes, but don't imagine it as being used for radar, but imagine the surface being covered with mirrors. You point it at the sun, and at the focal point you get a very high temperature. Depending on the size of your mirror and the geometry and that sort of thing, it could be anywhere between 600 and 1,200 degrees centigrade, something like that. But let's say 1,000 for the sake of example, which is a nice temperature to go for. All you do then is you put a 40-gallon drum of water at this focal point, and it superheats. Superheating just simply means boiling your water at a higher temperature than 100 degrees. And thermodynamics tells us that now if we run a steam engine off that steam, it will actually be more efficient than if it was just steam at 100, because you're now superheating it. And so you're approaching, getting closer to the ideal thermodynamic limits of efficiency here, which is what we want. This is what we want, to get good efficiency out of this thing. And of course, if you can run an engine of steam, you can run an electricity generator. You could use something like a Stirling engine, which has a good efficiency, and generate electricity using this technique. And so there's examples of this around the world. There are projects in California setting up these solar dishes. ANU in Canberra, Australian National University, have been working on this for years. Sandia Labs in America have been working on this sort of technology. The Spanish are into it. The Germans would like to be into it, but they don't have very much sun, so they're doing things like trying to set them up in Algeria and putting a high voltage DC cable all the way from Algeria to Aachen.
So can I just ask, how much land are we talking about? I mean,
to supply the whole world's energy.
Supply the whole world's energy using direct solar thermal.
Okay, so I did a couple of calculations. I first started off saying, well, let's look at the absolute worst case. What would be the most crazy amount of land we could soak up, just to see what the total limit is. And then, of course, with clever engineering, we could probably halve or quarter whatever that is. And so what I did, making some crazily generous assumptions, is I assumed a certain efficiency for the process, for the Stirling engine. I assumed a certain efficiency of the processes that would happen after we get that electricity. Like, for example, we might want to convert this electricity to hydrogen, for example, and then liquefy it. And so I looked at all the efficiency losses that would happen if you did all that, and then asked myself, calculated, well, what area of desert would that be? A typical, say, desert with an average solar irradiance of something like 300 watts per meter squared. And it turned out that it was only something of the order of 1,200 kilometers by 1,200 kilometers. So to put that into context, that is something that's about 8% of the surface area of all the world's great deserts. So it's a tiny... It sounds like a big distance, but it's a tiny amount on the grand scheme of things. Then I calculated what it would probably be more like without being so generous with all the inefficiencies. So with some clever engineering, we can bring down the inefficiencies. And so I calculated it was actually more likely in practice to be of the order of 500 by 500 kilometers. Which is, in fact, the whole area of the state of Victoria. So I hope there's no Victorians listening, but if we took over Victoria, I don't think we'd miss them. Just kidding. We wouldn't need the state of Victoria to do it, and it could be an equivalent desert area. Now, there's some interesting questions that are raised. It's a very small piece of land, but an interesting question is, would you really want to put the whole world's energy all in one spot? And I think not, because there's various good reasons for distributing it around the world. Like, you wouldn't, for a start, want one country to distribute the whole world's energy just for geopolitical reasons. We know the mess we've gotten into just because only a few countries can supply oil. So I think in reality, what we want to see are solar farms of the order of 1 by 1 kilometer or 2 by 2 kilometers, and many of them scattered around the world and not all in one place. And that would also be not only for geopolitical reasons, but also for distribution reasons of power. It would make it more economical to distribute the power. Security reasons, so if it's in one place, no one can just blow it up. It's distributed. And so on. So we can see it would be very sensible to distribute these things.
There are a couple of questions I've got for you, though. Fairly obviously, if we're talking solar thermal systems, it's fine while the sun shines. What happens when it doesn't? If you distribute it, then presumably you can move power around the globe. So, where sunny places send power to Paris by night and things like that. But is that the only solution?
Yes. So what you're asking is what happens at night time. Is that right?
Basically, yes.
Okay. So basically, because there's so much power at daytime, there's 10,000 times more than you really need. So what we can do is generate more power than you need at daytime and then store some of that power for use at nighttime. And so the question is, how do you store that? And so one of the least efficient ways to do it possibly would be just to simply electrolyze water and then burn off the hydrogen at night. We'll get to this later, but this is actually will be a good way for mobile, where you got mobile things that you need to power.
Which was the other question I was going to ask you. But we'll just put hydrogen on the shelf for now.
We'll come to that later, but it could, in theory, still be used for static cases like supplying at night.
Yeah. Now, they've been looking at things like, I think in Tasmania they were experimenting with vanadium batteries, fluid batteries. I think the Spaniards were looking at molten salt to store the energy overnight.
Yes. And also you can pump water to a higher level.
Well, that's the obvious way, isn't it?
And then let it go.
And use a micro-hydro generator
and you've
at
got
night.
hydroelectric power effectively, or you could use compressed air. And so I don't claim to have studied in all these energy storage techniques in a lot of detail, but there are technical papers out there that have looked at these things in more detail than I have. But even if one was to do it just by creating hydrogen, I found that that's what gave me the figure of 1,200 by 1,200 kilometers is the footprint you need to supply the whole world. That actually assumed hydrogen. I was doing
storage as well.
Yeah, I was doing a worst case there.
Now, presumably you're not storing the hydrogen as a gas.
I was liquefying it as well. And so even going through all that, it turns out that you only need 1,200 by 1,200 square kilometers. So hydrogen would be great for mobile things, which we'll get to later, but it's probably not so great for the static case where we just sort of want to burn something at night. And so the literature that I've read that's analyzed the storage problem appears to be of the consensus the two main contenders, the two heavy hitters, are the hydropower and the compressed air, as far as I can see. They seem to be the two biggies. I've done some small calculations and found that it's much better if you take an electric cable from your solar plant and send your electrical energy to somewhere else where you've got a suitable supply of water to pump it, rather than pump your water to the solar plant. That takes an enormous amount of energy. So it's definitely better doing it one way than the other. So my guess is that a good way to go will be the hydro method. You supply electrical energy via cable from your solar farm to some remote location that is suited for pumping up water to a high level and then creating a hydroelectric power. This is what I believe at the moment, though I'm still studying the storage aspects at the moment.
Well, that certainly seems reasonable. So, we talk really here about static energy. I mean, the other big part of the equation, of course, is mobile transport energy.
Yeah.
At the moment, that's predominantly provided by fossil fuels. Your alternative?
Okay, so I've thought a lot about this, and so you're generating all this electricity with solar power. So the obvious thing that comes to most people's minds is, well, we've got a great electricity distribution network. We've got all this electricity coming from solar power. Hey, let's just have electric cars and just plug them in. Unfortunately, it doesn't work. When I've done the calculations, I've found that each electric car would use something of the order of 20 kilograms of lithium. And then when you work out how many tons of lithium we've actually got in the world, it's not much. I can't remember the figure off the top of my head, but it's something of the order of 30 million tons of lithium, which actually isn't a lot. And then if you calculate the fact that we actually produce 60 million cars a year in the world, and just do a quick back-of-the-envelope calculation, we've only actually got enough lithium to last 23 years. So I think it's a bit of a non-starter there. So,
and that's assuming you're not using the lithium for anything else.
Yes, and the other important thing about lithium is every mobile phone and laptop uses it. And so I don't think we can afford to use up lithium for electric cars, because we got so many other useful things to do it with, to use it for. So then the question is, how else do we power our cars if it's not electrical? So the obvious thing is to do something chemical, is to use the solar generated electricity to create some chemical fluids that go in the car. And, you know, there's all sorts of things you can find in the literature, ethanol and methanol and all these oils, but they're all hydrocarbons again. Hey, let's get away from these things. So what I thought was the most simple and sustainable thing is just electrolyze water to get hydrogen and run your cars off liquid hydrogen. Now that
immediately raises some warning bells.
Yes. And
not the least of which is that liquid hydrogen would be very cold.
Exactly. So when I first considered this idea, I had lots of reservations myself, and I had my biggest worry is, look, is it safe, and how are we going to manage this? And it sounds a bit crazy. But then when I looked into it more and more, I began to see it really is the best way, and it sort of outstrips all the other methods. So let me go through some of the issues one by one and tell you why I think it's the best method. So first of all, before I do that, I think I should make a quick comment about hydrogen fuel cells, because this is the other alternative way to manage hydrogen in a vehicle. So for those of you who don't know what a fuel cell is, just to remind you, all it is a form of a battery. So it's a battery that's got chemicals in it, but you pour the hydrogen in the battery, and this is what basically gets the chemical reaction going, and the battery creates electricity that powers your electric car. And again, it's all going back to toxic chemicals, and I just really don't like that, because then when you multiply that by the number of cars, it's a lot of chemicals in the environment. Surely, if there is a way to do it with liquid hydrogen, it would be the best, because when you burn liquid hydrogen, it turns back to water. And water is the safest, cleanest thing on the planet, and there's lots of it. So this is the ideal. If we can get it to work, this is definitely the way to go. So the question is, how do we get it to work, and what are the issues? So which one would you like me to talk about first? Do you have a preference? Shall I talk about safety first?
Shall we start with the Hindenburg?
Yes.
Yeah, you talk hydrogen, that's what everyone thinks of.
Okay, so let's talk about safety. So for those...
I'm a big fan of the Zeppelin.
Yes. So for those of you who don't remember the Hindenburg, it was basically one of those huge dirigible balloons that had a little gondola underneath it with lots of little people, and it just floated through the air. And it was made light because this huge balloon had hydrogen in it.
Well, we should point out that, it's not just a balloon because it was powered flight.
Yes.
And the Hindenburg was doing a regular transatlantic
yes.
service. So,
yes.
It was in regular service.
I was trying to explain that the hydrogen was used to make the whole thing
provide
float.
the lift.
Yes, to provide the lift, the buoyancy. So, as people know, the Hindenburg went on fire, and
1937.
In 1937, it crashed, and so that raised alarms in people's heads about hydrogen and its safety.
I should perhaps point out that not everyone died in that crash. In fact, quite a good proportion of people walked away.
That's right. This is what I was about to come to. So the urban myth is that this hydrogen balloon, because it was hydrogen, it just went kaboom and everyone died. But this is not true at all. What happened is it didn't go kaboom. What happened is there was a fire on the top surface of the balloon, and the hydrogen was just gradually burning off, and the balloon just floated down, and 67 people walked off into safety. Out of 91. So there were a few people that died. Some of those were because they got scared and jumped too early. Some was due to the fire. But as many as 67 walked away to safety. So it wasn't as dangerous as one might imagine.
As opposed to a modern airline crash.
That's right. A lot more people die in a modern gasoline aircraft crash. So let's put it into some context here. So now, other issues. So what happens if you're driving a hydrogen car and you've, say, got a puncture in your fuel tank and you ignite it? What happens? So the University of Miami did a wonderful study on this. And they got two cars side by side, one with normal gasoline, petrol, and one with liquid hydrogen. They punctured both the tanks and set light to them. They took a video of this as this was happening, and 3 seconds into the video, what you see is the petrol car has got flames all underneath it because the petrol is heavy, and it's gone down underneath the car, and it's all aflame. But the interesting thing about the hydrogen car is you've got this very narrow flame going vertically upwards, a very tiny narrow flame. And the reason for this is hydrogen is 15 times lighter than air, and so it goes up in this wonderful little stream and it just burns off. And so then 60 seconds into the video, what do you see? The hydrogen car is standing perfectly in its pristine condition, just
minus one ruptured fuel tank.
Just with one little burnt off fuel tank. It didn't explode. It just burnt. Just gradually, the flame just burnt off. What do you see 60 seconds later in the petrol flame car? The whole car's incinerated. So, if I was in the petrol car, if I was the driver in that car, I would be asphyxiated to death. In the hydrogen car, I'd be perfectly safe. So I think one can look at all these factors and put some of these safety issues into context. Another interesting test that was done at Lawrence Livermore Labs in America is they took a hydrogen tank that was used for our liquid hydrogen car and bathed it in flames for 60 minutes and also shot it with armor plate piercing bullets, .3 caliber, and did all. I mean, only in America would you have bullet tests like this, but and and there was no explosion or anything. So what the hydrogen just safely leaked out through the little safety valves that are in the tank.
It's worth pointing out, I think, there are in fact vehicles currently in production using liquid hydrogen as a fuel.
That's right. The BMW have a car called the Hydrogen 7, which runs totally off liquid hydrogen. Although it's in production, it's I should say it's a sort of pre-production model in that they're only producing 100 of them and giving them to celebrities around the world to try them out and to promote them, and then the plan is to go and start churning them out. And these BMWs perform perfectly well. They've solved all the various problems, like how do you keep the liquid hydrogen really cold in the tank. They basically use a principle of a dewar, so they've got a double wall tank. And it's made out of a very simple material. It's just a composite of aluminium and glass fiber. It's nothing fancy. And they say in the literature that if you were to put a cup of hot coffee in their tank and close the tank and came back 70 days later, your cup of coffee would still be hot. The insulation effect is that good.
Now, what temperature is liquid hydrogen at in these systems?
It's of the order of less than minus 200, so it's pretty cold. It's pretty cold. But, what the energy required to actually liquefy your hydrogen, because it's coming from these solar collectors anyway, it just means you put a few more solar collectors up in your big collection, in your solar farm. You maybe have to put 20% more, but it will give you that power to then go and liquefy the hydrogen.
Which then gives you a fuel source for your mobile energy needs.
Which gives your mobile energy
and
needs.
Also potentially a storage mechanism for excess solar during the day.
Exactly. For the excess solar, you probably want to use the hydro method, but it could be used if you wanted to. Now, what are the other issues with liquid hydrogen that I should mention? The other interesting thing is there are some questions about emissions. It turns out that when you combust your liquid hydrogen internal combustion engine in your car, it can react with the lubricants in your car, and so can create carbon monoxide. But these have been measured, and the levels of carbon monoxide that actually come out are extremely low. They're actually of the order that carbon monoxide naturally exists in air anyway, so it's that sort of level. So it's way below the level of normal gasoline engines. So that's nothing to be too concerned about. Also, because it's being combusted in air, which contains nitrogen, there's some concern that you would get nitrous oxide products. And there again, it turns out that the nitrous oxide products is extremely very low. If the engine is running in its correct regime, in its efficient regime which you want it to, it turns out the nitrous oxide emissions are less than 4% of the super ultra low emission standard, and so it's way lower than what you presently get with gasoline engines. So you're way under what gasoline produce. So it's looking all good there. What other issues? Then there's issues with how do you electrolyze the hydrogen efficiently? And so efficient electrolyzers use platinum electrodes. And what I've done is I've done a calculation to calculate how much platinum you would need to electrolyze enough hydrogen to supply 15 terawatts or the whole world's energy needs, just as a hypothetical. And you wouldn't, of course, supply all the 15 terawatts with hydrogen. You'd use electricity as well. But if you did, you would use more than 2 times all of the platinum that exists in the world. So you couldn't do it. So this suggests that we should move away from platinum electrodes and look for alternatives. And so in my calculation, where I calculated the footprint of this solar collector farm for the whole world, it should be 1,200 by 1,200. I was assuming a very poor efficiency for electrolysis for not using platinum but using a baser metal in that calculation, showing that even if you didn't use sophisticated platinum, it's still tenable. So that's an interesting thing that came out there. Another interesting consequence of hydrogen is the one thing you have to consider is that when you handle hydrogen, you're going to, because you're human, some of it's going to accidentally get released into the air as you handle and transport the hydrogen. Usually tanks that have hydrogen have little bleed-off valves which go into some sort of catalyst, so it turns it back to water. But if hydrogen is released into the air, one of the things that can happen is it can go right into the troposphere, and some of it can even be released into space because it can escape gravitational attraction. A very small amount goes into space. And so one question is, well, if we have a hydrogen economy, will it last? Because won't we deplete all our oceans in the world if we keep electrolyzing them? Because we're losing a tiny amount of hydrogen every day if we all convert to hydrogen. Well, I calculated that if we were to supply our whole world's energy needs, all the 15 terawatts with hydrogen, it would last 1 billion years, provided we didn't lose more than 5% of our hydrogen to the atmosphere. The industry standard at the moment is we don't lose more than 0.1%. So that's very good. We should be able to maintain that and be well within our billion-year limit. So it's got billion-year viability. Just a very, can I mention one cute last thing?
Just enough, because we're reaching the limits of our show here.
Okay, one cute thing is it turns out that comets, these are very small comets, hit our planet every 3 seconds, and they contain lots of water. And I calculated how much water the Earth actually receives from comets. And it turns out, according to my calculations, that in 1 million years, we're going to flood all coastal cities in the world because we receive too much water from these comets. And so my final punchline is that we need a hydrogen economy to stop ourselves flooding in 1 million years' time. And we actually need to deliberately leak more than 0.1% out. We need to leak 1% so it balances.
Tremendous. Thank you very much. I've been speaking to Professor Derek Abbott from the University of Adelaide, the Electrical Engineering Department, and we've been looking at the long view in moving to a sustainable energy economy using solar thermal and hydrogen. And we're just about out of time. We'll see you next week with another Environment Show.